Okay, so good afternoon, everyone. I hope you see my slides. And my pointer here. So today I want to finish a few things that we were talking about for fun, about relativity. The idea was to justify what is the minimal coupling between electrons and an electromagnetic field, and also to show how to get relativistic wave equations, especially the Dirac equation, and make a connection with graphene to come back to our issues. Having done that, I would probably be able to start with the main section of these lectures, which is dealing with elementary excitations in solids. And that's because the ultimate task we set is to understand electron transport in crystals, in semiconductors in particular. And clearly, transport is controlled by scattering of electrons with various things. And these various things are actually elementary excitations. So this will be the main novel ingredient in our lecture. So let's go back a little bit. We were talking last time about some basic ideas about special relativity, mainly when we'll deal with interaction of electrons or matter with light, so electrons with electromagnetic fields. We'll have to find what is the coupling between the electrons and the electromagnetic field, and we will use something which is called the minimal coupling, and this comes from special relativity, so that's what I have in mind to show, and we'll do it in a minute. We discussed a little bit the fact that at the end of the 19th century, there was a problem. Newton's laws seem to be invariant, well, are invariant under Galilean relativity, Galilean transformation, which means that different observers moving at constant velocity with respect to one another will describe the physical world using the same equations, which has algebraically and mathematically the same form, such as F equal ma, for example. And this equation is indeed invariant if you move with some velocity u with respect to another observer, which also uses the same equation to express things. And that's because we have a second derivative, so if we move at constant velocity with respect to one another, the second derivative dies and this u disappears. The problem was that Maxwell's equations do not do that. They do not show the same property. I think I've hinted in some past lecture the fact that it's pretty obvious that something is amiss if you pick a Galilean idea, and that's because we saw, for example, for the Lorentz force, that an electron feels the force with a magnetic field, and this is proportional to the velocity. So if we move with the electron, the velocity goes to zero, something must be happening, which is not accounted for by Galilean relativity. And indeed, if you go and try and write a wave equation and convert it by shifting from one reference frame to another, you don't get the same expression. And that's because it's a different, if you want, faces of the same problem, which keep popping up. The electric and the magnetic field are not really different objects, but they have to be lumped into a single object, which will be invariant under different type of transformations. So I think I said last time that the choice that physicists had was to discard Newton's laws, to discard Maxwell's equations, do something in between, which is what most people did, which is to assume that Maxwell equations are valid only in a particular preferred frame of reference, in which this hypothetical fictitious medium called ether was at rest. And whenever you move away from this frame and you move with constant velocity away from this frame, things change. Maxwell equation will not have the same form. Clearly not a very satisfactory answer. And indeed, it was Einstein that, having to choose between these three different options, took the observation that the velocity of light is the same regardless of your velocity, the velocity of the observer, I gave the example of the Murchison and Morley experiment. I'm not sure if that is historically totally correct. Logically and pedagogically it's nice, but things are a little more complicated from a historical point of view. But anyway, he started considering what is the consequence of assuming that if you have at time t equals 0, at x, y, and z equals 0, at the origin of a frame, you have a light, a spherical source of light, and the wavefront propagates with velocity c. So this is the equation of a sphere, surface of a sphere, which expands with time, with velocity c, velocity of light. A frame which is an observer, which is moving with a constant velocity, and so it has a different respect to the first observer, and has different sets of coordinates, has to see exactly the same situation. Clearly, Galilean relativity does not give you that, because, as we said, the velocity of light will be different in the two frames if we stick to the Galilean principle. Instead, things are different, and the major thing that nobody had considered before was that not only the spatial coordinates transform, but also time transforms. And the only way we can achieve this situation, we can describe this spherical wavefronts as being the same for both observers. I called K and K prime, these two frames that move at velocity u with respect to one another. The only transformation that you have is something that mixes time, which I call x0 here, which is ct, and space. And the transformation is given by this law. So, and that's what we described last time. We saw that this has some consequences. The main consequence is that time flows at different speeds depending on the velocity of the observer. So two observers will not have time which flows at the same speed. And in particular, it's very useful to define the proper time. So if we have a particle which is propagating at constant velocity along some directions, it is convenient to use the clock that gives you the time as it flows at the speed that the particle sees, which is called the proper time tau. And this time clearly can expand or contract depending on the speed of the observer which looks at this particle. And I gave the example, an experimental verification of this fact, that the mu lepton, at the time was called meson, has a lifetime of about 2 microseconds. It is generated by cosmic rays in the upper atmosphere, some 100 kilometers up in the air, and yet they are detected at the ground level, at sea level. And that's because these particles move at a speed which is very close to the speed of light. So time for them flows very slowly with respect to what is the flow time as seen by an observer at sea level. Okay, now, one thing that you can also see is that given these transformations, the velocity of a particle which is seen by an observer which is moving velocity u with respect to another observer in the frame k, the velocities will not add up exactly in the same way as you would guess intuitively. This explains the paradox that the speed of light has the same velocity, has the same value regardless of the state of motion of the observer. And you can do a little bit of algebra here and see that actually the velocity of a particle v as seen by an observer becomes a velocity v prime seen by another observer which is moving with velocity u, constant, everything constant with respect to the other observer. If you can ignore this factor in the denominator when both v and u are very small with respect to the speed of light, you recover the usual additional velocities. If I'm traveling at 50 miles an hour against another car which travels at 50 miles an hour, the relative speed will be 100 miles an hour. But if the velocities begin to approach the speed of light, then there is a correction factor, and when both become c, you still get c. There is a factor of 2 in the denominator, which cancels the factor of 2 that you would have in the numerator. And this explains the Murchison and Morley observation. Now, what I'd like to drive now to is the final object, and we will essentially have to find an expression for the total energy of the particle. We will need that in order to discuss relativistic versions of Schrödinger equation, possible relativistic versions. So the idea is, how do we express the total energy of a particle in terms of its momentum, or its velocity, if you wish? So the general procedure would be to say, well, I want to generalize F equal ma, essentially. I want to generalize it because I know that F equal ma is invariant under Galilean transformation, and instead now we're using different transformations, which again mix space and time. So actually there is an interesting derivation and proof in Jackson's book, Classical Electrodynamics. What you want is to generalize and say that the total energy of the particle and its momentum will be functions, general functions, homogeneous of the velocity of the particle. And you can actually impose the limit. You know that the second derivative of the energy with respect to the velocity in classical mechanics has to be 1/2 m. Oops, I'm sorry. So this is something that we need in order to recover Newton's laws when the speed of the particle is very small. We know also that the mass of the particle with its velocity 0 has to be what we shall call the rest mass of the particle. And we can see that the only form that this generalized expression can have is if we write the mass of the particle that moves at velocity u as the rest mass times this factor gamma. I remind you what gamma is. I had it here somewhere. Is this object. Gamma is 1 over the square root of 1 minus v squared over c squared. So that this gamma becomes, it tends to infinity when the speed of the particle approaches the speed of light. So the mass of the particle, if you want, grows as the velocity of the particle increases. And the energy of the particle will be this product, famous product, mc squared, times this same factor gamma. And one can show that indeed when the velocity of the particle goes to 0, you recover essentially the kinetic energy of the particle in Newtonian mechanics, plus this rest energy, the famous rest energy mc squared. In order to express now something in terms, this energy in terms of a 4 vector, remember we're moving now in space-time, since space and time are mixed by the Einstein's transformations. Everything has to be invariant when we essentially do, let me call it a rotation in this 4-dimensional space-time. It's a funny space-time with the dot product, which is as a minus sign in front of the whatever you wished, however you wish to express it, in front of the time component or the spatial component. So we can express everything in terms of objects, vectors that transforms correctly under these transformations, these Lorentz transformations. And the object that we're interested in is the 4 momentum, the 4 vector of the, let's call it energy momentum, whose time-like component is just the energy of the particle divided by speed of light. And its momentum is essentially the generalized version of the linear momentum that we have in classical mechanics, just m times v, or u, the velocity, but there is this factor gamma in front. The magnitude of this 4 vector, remember that we have this funny metric, plus, 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 minus, is just m squared c squared. So the energy of the particle, the total energy now in terms of its momentum, it's something slightly different, well, quite different from what we had in Newtonian mechanics. We'll need this, as I said, to obtain some relativistic versions of Schrödinger equation. And we have a problem because of the square root that we have here. I'll discuss it in a minute. So this is some expression that we have to keep in mind. And as I showed before here, actually, we recover Newtonian mechanics when the speed of the particle is very small. Good. Now to the minimal coupling. Again, that was another of the goals that I had in mind and why we are spending our time in relativity. So what we want to do now is to take the Lorentz force, which is F equal ma in the presence of, for a charged particle in the presence of an electric field and a magnetic field, and convert it into something which is invariant under this new set of transformations. Again, I mentioned before that something is very different from Galilean relativity because E and B have to transform to one another when I change the velocity of the observer. For the reasons that I showed before, not only because of the Lorentz force. Again, if I move with the electron so that U goes to 0, the force that I get here has to be transferred somewhere else. Also, we know that a moving charge generates a magnetic field. What happens to that magnetic field when I look at the particle at rest? So I move with the particle. Clearly, it has to go somewhere else. And indeed, the idea is to generalize this into these three equations, make them four equations. So the three spatial or space-like components of my new expression for the Lorentz force will be these. In addition, I add, if you want, the energy balance, so that the change of the energy of the particle with respect to the proper time of the particle must be equal to Joule heating, if you wish, just the work done by the electric field on a particle. So I write them now in terms of what I defined as the four momentum that we defined before, and define these four equations. These are the three space-like equations, exactly what I have here. And then I have the energy balance, if you wish, for the time-like component. Now, in order to make it the typical expression that people in relativity use is a manifestly covariant, so to show that indeed the equation transforms in a correct way when I change the reference frame. I can define now an object, which is what I already hinted, which is an electromagnetic tensor. It's a second-rank tensor, which has components which contain both the electric and the magnetic field. And by the transformation laws from special relativity, clearly the electric and the magnetic field are mixed. But the good point that I want to make is that indeed we can write the Lorentz force plus this energy balance in terms of a set of four equations, which are manifestly covariant under transformations. The important thing that I want to make is that if we want to derive these equations from Hamiltonian, so if we go to the Hamiltonian formulation of mechanics and find what Hamiltonian gives me this equation as Hamilton equation of motion for this momentum, the Hamiltonian that we have to use as this form. I think it's kind of intuitive. If we forget the vector potential and the scalar potential, this is just the Hamiltonian of a particle, which just c squared p squared plus whatever is this object over here, the rest energy. Now I have a 4 vector, which is the momentum energy. So the p plus the energy of the momentum and the energy of the particle is a 4 vector. The electromagnetic field can also be described by a 4 vector. The 3 space-like components are the vector potential, such as the curl of A is equal B, as usual. And then I have the scalar electrostatic potential, which is the time-like component, if you want. So now all we do is to add to the spatial components the 3 space-like components of the vector potential, and to the energy, to this total energy of the particle, the time-like component of the 4 vector. And so this is where this idea that what we call the minimal coupling, that in order to look at how an electron couples, or any charged particle couples with an electromagnetic field, is obtained by adding to the momentum, of the classical momentum of the particle, the canonically conjugated momentum to the coordinates, the vector potential. And these are various units. If we are using Gaussian units, there will be C and so on. And to the total energy, just as usual, the electrostatic energy, if you wish. So this is where the famous minimal coupling comes from. It comes from writing the expression for the Lorentz force together with an expression for energy balance in terms of Hamilton equation for a 4 vector, the 4 energy momentum vector, and then looking at what is the Hamiltonian that I have to use in order to derive my expression for the Lorentz force plus energy balance in terms of the Hamilton equation of motion of this form. So that was one of the main goals to go to deal with special relativity and see where this is coming from. Now, the second goal that I set originally was, graphene. Usually people say it's the electron dispersion of graphene close to the Fermi level, which is where the conduction band and the valence band touch, is given by approximately by a Dirac equation for a particle of zero mass. Where is this coming from? So the idea is now to try and derive, to show where the Dirac equation comes from. It comes from the idea that immediately after quantum mechanics had been invented, discovered, you choose the word that you prefer depending on your philosophical view about theory of knowledge, we have to generalize Schrödinger equation. Schrödinger equation is not relativistic. Let me be a little bit paradoxical here. I think that Schrödinger derived his equation by just writing the energy is equal to the energy, but then writing the energy in two different ways. One is writing the energy of the classical particles in terms of its momentum, and the other is looking at the energy as the generating function of translations in time, so the time derivative. And so you set p squared divided by 2n. This is for a particle in free space, no potential. If p becomes the generating functions for translation in space, this becomes the Laplacian, and this is equal to the translation in time. So essentially, we're starting from the non-relativistic expression of the energy, writing it in terms of either, as I said, translation in space or translation in time, and this gives a Schrödinger equation. I have no idea if that is what Schrödinger thought, presumably. Now what we have to do is generalize this, replace this expression, which is the classical expression for the energy of a particle in terms of its momentum, with the expression that we have from special relativity. It's a problem. If we just do it naively, brute force, and follow this argument that I just gave you, we're stuck with a very nasty operator, which is not even continuous in any Hilbert space of well-behaved functions that you can think of, because of the square root. And this is a real nuisance. And that's what created problems when people started generalizing Schrödinger equation to a relativistic situation. So there are two ideas that one can have. The first idea is the obvious one. Well, I don't like square roots, so let me square this. And write the square of the energy, which will become a second derivative in time, is equal to the Laplacian that I have from same stuff that I have from Schrödinger equation, because I get rid of the square root. So this is something that we can do. Indeed, this is what I wrote here. So I squared that expression, the relativistic expression for the energy of a particle in terms of its momentum and its rest mass, and I make this equal to the time derivative, with the units and the minus sign, which comes from the I that I have here, of course. And this gives me this equation, which I can rewrite it like this. If I define as this square, the D'Alembert operator, the D'Alembertian, which is just the second derivative with respect to time minus the second derivative with respect to space, so the Laplacian. This is called the D'Alembert operator. Notice that I flipped the sign of the metric here, in which I have a plus for the time and the minus for the spatial coordinates. I can rewrite it this way. Usually in relativistic quantum mechanics, people tend to use units in which the speed of light and h bar are equal to 1. So all this stuff becomes 1, and I get this expression, which is called the Klein-Gordon equation. I'm not sure if historically that was exactly the first relativistic equation which was proposed. There are problems with this equation. If you view it as a wave equation, the same way you view Schrödinger equation as an equation for a wave function. So now this becomes a relativistic wave function for a particle. You can solve it. You can find that still you have plane waves. Everything is okay. There is one complication. And the complication is its interpretation. First of all, since I've taken the square, you expect positive and negative energy solution. This is something that we will see also for the Dirac equation. You have states which propagate in time. They are plane waves in absence of a potential, but states can have both positive and negative energy. And one can say, okay, let's attribute the positive energy solution to a particle and negative energy solution to its antiparticle, which is what Dirac did for electrons and positrons. There is a problem in the sense that if you now look at a probability current, probability flux, which now becomes a four-dimensional vector, and you interpret the time-like component as a probability for a particle, which is corresponding probability flux, which is given by the three space-like components of this current density, probability current density, the probability gets negative values for negative energy particles, because it's exactly twice the energy of the particle times the squared of the wave function. And that's a problem. One can say, well, so let's ignore negative energy solutions. The problem is that whenever you add a potential, you add an interaction between particles, negative and positive energy solutions mix. And then you really do not know what to do. So if you interpret this equation, as I said, in a conventional matter, where this is a wave function now, and you give the usual Copenhagen interpretation to this wave function, you run into problems. Your usual interpretation that you were able to associate without any internal inconsistency to Schrödinger equation cannot be done from this equation. You can interpret in a different way, which is as a quantum field. That's what we're going to do next. And then the problem doesn't disappear, but it becomes solvable. And indeed, sometimes this equation, the Klein-Gordon field, interpreted in this different way, can describe a spinless or zero spin particles with mass n. But for electrons, that doesn't work. So what did Dirac do? So we don't like square roots. And as I said, the first idea was to square it. And this gives us problems. So Dirac had an idea which actually goes back to Hamilton, or the so-called quaternion algebra. So let me just deal a little bit with algebra now. We know that a squared minus b squared is just a plus b times I minus b. If I want to factor a squared plus b squared into two pieces, so factor this polynomial into two terms, I can do it, but I have to go beyond real numbers. I need I, the imaginary unit. And then I can write this expression in terms of a factor of two first-order terms. Dirac wanted to do the same thing for this expression. The complication is that I have 1 plus 3, 4 components. So essentially what I want to do is to be able to factor these three space-like components. I call them in generally 1a, 2a, 3. A time-like component, which is the mass b squared. I want to write it as a factor of two terms, where this becomes sorry, I had a problem here. This actually should be a minus. I did a mistake here. This should be a minus, okay? This symbol's over here. I want to write it to factor it in some form like this. This is a problem that actually, I think the correct term would be obsessed Hamilton. I heard the story, I read it somewhere, I don't know if it's true, that Hamilton thought about how to factor this thing. These are called quaternions in this form. Clearly, with numbers, you don't get it. In order to get this expression factored this way, I don't know why. Did I write it correctly somewhere else? No. I think I had the wrong version of the slides. Anyway, in order to factor it in some form like this should be minus I gamma 1, minus I gamma 2, minus I gamma 3. And there should be an I multiplying this thing. In order to do that, you see that you have to, when you do the product, you get also all the cross terms, gamma 1, gamma 2, gamma 1, gamma 3, and so on. These terms have to cancel, which means that gamma 1, gamma 2, gamma 1, gamma 3, gamma 2, gamma 3 have to anti-commute at the gamma 0, 2. Clearly, with real numbers or complex numbers, you don't get that. You need different algebraic objects that do that, and they were called quaternions. The story goes that Hamilton was obsessed with this problem. One evening, he was in Dublin, I guess he lived there, and he went to a pub. He had perhaps one beer too many, and coming back, he had an epiphany and found out what the solution is. These must be 4 by 4 matrices, and they can anti-commute. And then I solved the problem. he was drunk. He was afraid of the fact that waking up the next morning he would have forgotten his idea. So he was crossing a bridge and he put a pebble and started scribbling something about his idea, scratching the stones of the railing of the bridge. I don't know if this history is true or not, part of the legend. But anyway, Dirac knew about this story clearly, and so he thought that indeed, instead of squaring, as we said here, right? Let's square this expression so that we get rid of the square root. Why don't I write this as a product of those two factors of the polynomial? So essentially, I'm taking a sort of a quasi-square root. And the idea is that indeed the Hamilton's matrices or the quaternions are these matrices. These sigmas are the Pauli matrices that we saw for spin. Gamma 0 is just similar to the identity matrix, except that there is a minus sign here. These are 2 by 2 identity matrices. These are the 2 by 2 Pauli matrices. And let's define these 4 by 4 matrices, which are given by these expressions. If you do that, then you can see that indeed the gamma I and gamma 0, they all anticommute, so that when you try and factor this term into two pieces, they actually factor out correctly because all of the cross terms vanish. So this is what I wrote here. Okay, so the idea is that now, having done that, I can replace P or P mu, P0, which is the time derivative, and P1, 2, 3, which will be the 3 derivatives with respect to the 3 space coordinates. I can write it in terms of the derivative with respect to x mu. The standard notation is, in this case, I use mu as going from 0 to 3. The notation is very complicated. Sometimes people lump an I inside the time component so that you have a metric which is plus 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 rather than plus minus minus minus. There are various versions, so mu runs from 1 to 4. I stick to this notation in which my metric will be given by a plus when I take the square of the time derivatives or the time component, time-like component of a vector, and minus when I pick the spatial components. So the P becomes a time derivative or spatial derivative, depending on what mu is. The mu is the usual Einstein's notation in which I imply that the sum over a repeated index is performed. In units in which h bar and c are equal to 1, it takes this form. Restoring all the units, it takes this particular form. And this is now an equation, which is actually a set of 4 equations. So my wave function now is a 4 vector. Not surprisingly, we're doing relativity here. So there is well, let me explain what the 4 comes from, which is very interesting. Anyway, we can see that if I take this expression and multiply it by expression in which I change the sign here, I recover, with a little bit of manipulation, I recover the Klein-Gordon equation. So indeed, the Dirac equation is, in some creative interpretation, is the square root of the Klein-Gordon equation. And so the unknown now becomes a 4 vector. And that's where things get interesting. These 4 components can be interpreted as positive and negative energy solution for particles which are described by a 2 vector. The 2 vector for the positive energy and 2 vector for the negative energy solution. And the 2 vector clearly is interpreted as a spinor. So spin is introduced, I think, in a way which, I guess we'll agree, is much better than the ad hoc way in which we had to introduce it into Schrödinger equation. Schrödinger equation has nothing to do with spin. We have to add it manually. Here instead, in Dirac's formulation, spin comes naturally from the way the equation has been derived. So we can go now and look at a solution of the Dirac equation. I'm not going to go through all of the details. It's in a slide. If you're interested, you can look at it. There are 2 interesting things that I would like to discuss. First of all, if we deal with a particle which has 0 mass, it's easy to see that the solution can be written in a simple form. I will use this form with this zeta sec sigma, where sigma is 1 or 2, is just the vector 1, 0. And sigma dot k, dot k unit vector along the direction of k, is the projection of the spin along the momentum of the particle, which is sometimes called helicity. For a particle which moves at finite velocity, velocity smaller than speed of light, you can change it depending on the observer. Clearly, if you overcome the particle, you change its helicity. For particles which move at the speed of light, like neutrinos, which were thought to be massless for many decades, you cannot change it because you cannot overcome a particle that moves at the speed of light. But this is an interesting form for the solutions of the Dirac equation when you put a zero mass. By the way, there are, as I said also last time, there are two forms of the equation that you can find for spin 1/2 particles at zero mass, depending on whether you require that the wave function is equal to its charge conjugate, which is the compass conjugate multiplied by the change of the charge. And one, when the particle is equal to its antiparticle, is called the Majorana equation, which was the first equation which was proposed for neutrinos. And the opposite case is called the Weyl equation. Anyway, two interesting consequences of the Dirac equation. One is, if you want, a curiosity, although there is some interest now in some two-dimensional materials and topological insulators. If you take the Dirac equation, you rewrite it in this form. When I define these matrices now, beta is just gamma 0, and alpha are the three matrices, the gamma, spatial like gamma, multiplied by gamma 0. You can rewrite it as a sort of Schrödinger equation, but it's relativistically covariant. And then you can define the velocity. You find that this is equal to this matrix is alpha, each component x, y, z. You can plug it into a Heisenberg equation of motion for this alpha, integrate it. I've skipped quite a few steps here. And what you find is that position of a particle as a function of time is given by position at time equals 0, plus its velocity, okay, written in some strange terms here, but it's something which increases with time, so a velocity. But then there is a funny term, which is oscillating. It's an oscillatory term, which is called with the German term Zitterbewegung. And it looks like the particle is moving at a constant velocity, but then there is a little bit back and forth motion of the particle around its position, and this for all of its coordinates. So it kind of loops around itself. I don't know if it has ever been seen. I've read recently that some people were looking for this Zitterbewegung in materials in which the electron dispersion can be described, as I'll show in the next slide, by a massless Dirac equation. And this is graphene, which is the first example that people saw, but also in surface states of three-dimensional topological insulators or edge states of two-dimensional topological insulators, so in ribbons. And people are looking and see if they can observe this Zitterbewegung. I may mention later on what topological insulators are for those who don't know. The other interesting consequence of the Dirac equation is if you plug it into in an electromagnetic field, it's quite laborious. So again, I don't go through the derivation here, but you can find essentially that you can Schrödingerize the Dirac equation, write it in some form which resembles Schrödinger equation for a particle in the presence of a magnetic field. But the interesting thing is that in front of spin, you get the magnetic moment, if you want, of the electron for spin, you get an extra factor of 2. I hope you remember when we were discussing the spin-orbit interaction, I gave the straightforward expression that you get from classical electrodynamics for the magnetic moment of a particle with a given angular momentum. And I said, actually, we're making two mistakes of factors of 2s. And one of them was the fact that the magnetic moment of the electron is almost twice as large as it should be. It's actually 2.0032, whatever it is. The Dirac's equation actually gives you exactly a factor of 2, which we know is not exact. There is some correction to the third decimal figure and beyond, and that has to be dealt with quantum electrodynamics. But this is another interesting result that comes for free from the Dirac equation. So the Dirac equation gives you spin in a natural way. It gives you this anomalous gyromagnetic moment of the electron. And of course, what Dirac was enthusiastic about was, excuse me, it predicts an electron and an antiparticle, which was associated to the negative energy solutions. Okay, I'll stop here with relativity just to make a connection with graphene. If you go and do, as I'll show in the next slide, if you want to find a simple tight binding model for graphene, you can write the Hamiltonian in a way that is similar to a Dirac equation in 2 dimensions now, because we're dealing with a 2-dimensional situation. The gamma matrices becomes just the Pauli matrices, and this looks very much like the Hamiltonian for a Dirac particle. If you replace these k vectors with the derivative respect to x and y, you get exactly the time-independent Dirac equation, which gives you a dispersion, which is the usual Dirac cone. So it's like exactly like light, except the speed of light is replaced by what's called the Fermi velocity. So it's a different slope. What you can do is only to derive it this way, is to just formulate, let me write it here. You can, well, let me explain it here. You can look at the graphene, which is this hexagonal lattice, as a combination of 2 sublattices, triangular sublattice, sublattice A and sublattice B. You can write the usual tight binding expression for the expectation value of the energy on the ground state wave function, which are just the pz orbital. Remember, every carbon atom has a 4-fold coordination. 3 of the 4 atoms, 4 electrons, are hybridized into an sp2 bonding configuration, and then we're left with a pz orbital, which is the orbital sticking out of the plane, which hybridizes into the pi band. So we look at interaction of these pz electrons in the sublattice A interact with the sublattice B. So we can write the nearest neighbor interaction in terms of these vectors deltas, delta 1, delta 2, delta 3. So each atom in a sublattice A interacts with atoms in a sublattice B, and the overlap energy between these overlap functions, the pz interaction, is labeled empirically by parameter T. It's not time, unfortunately, that's a standard notation. I think it's about 2.5 electron volts or something like that. And so you can express the expectation value of the energy, so the band structure of these 2 sublattices interacting one with the other in terms of a 2x2 matrix. And this, again, you can express it in terms of the Pauli matrices. And that's where you get this Dirac, massless Dirac expression for graphene. And I think that's why people are interested in looking at whether in graphene you can actually see something like the Zitterbewegung, because solving that equation for the velocity of an electron, the group velocity of an electron, you will also get that behavior. Okay, any question about this stuff? Am I still online? Do I exist? Yes? No?
Yes, you do.
Online? Yes, you do. I exist. That's good. It's good to know. Okay. So let me finally get back to something which is the core of this class. So let me start with a funny thing that I usually ask my students. Suppose that I have an hydrogen atom and I've excited it somehow with light thermally by kicking it with some collision. And its electron is in a 2p excited state. All you know is conventional quantum mechanics. So I ask my students, what happens to this atom? And invariably everybody says, hey, it decays. This electron decays from the 2p states to the 1s state. And I said, wrong. I mean, right, yes, we know that that's what happens. But knowing what you know from conventional quantum mechanics, this shouldn't happen. The 2p state is a stationary state. It's an eigenstate of a Hamiltonian The only potential I have here is the potential of the hydrogen nucleus, which is a static potential. So there's no perturbation. I'm solving exactly the problem in my hydrogen atom. I have an electron in a 2p state. It should stay there forever. There's nothing that can trigger an excitation to decay from its excited state again to the ground state. Now we know that even before quantum mechanics was invented or discovered, again, I'm not going to go into it. In 1916, actually, Einstein did a study of, and that was related to the black body radiation. What happens if you have atoms, and we knew from I think 3 years, only 3 years old, Rutherford experiment, right, 1913, if I'm correct. We knew what atoms look like. How do atoms and electromagnetic radiation reach equilibrium? And looking essentially at statistical mechanics, or if you wish, thermodynamics, probably statistical mechanics is better, Einstein concluded that in order to reach equilibrium, you must have 3 types of processes that can happen in an atom which is excited. You can have excitation, so absorption of a photon, absorption of light. So the 1s electron goes to a 2p. By the way, p and s are coupled because we know that electromagnetic radiation transitions triggered by electromagnetic radiation have to have a change of angular momentum of plus or minus 1. So we go from L equals 0 to L equals 1 here. So we can have absorption, and this is a process that has a rate which has to be proportional to the number of photons that I have around. And this is quite obvious. Clearly, the probability that an electron absorbs a photon and jumps to an excited state is proportional to the number of photons that I have around. Makes sense. A little less intuitive is the fact that I can have emission from 2p, say, to the 1s, which also has to be proportional to the number of photons. And that's a little bit strange. Why should I have that? In addition, there should be spontaneous emission. This kind of makes sense, although if you think about it, the idea of quantization of the hydrogen atom came exactly, so quantum mechanics, but the early Bohr-Sommerfeld quantization idea, where in order to prevent this decay, we knew that the solar system model of the atom classically did not survive scrutiny, because an electron which is accelerated when it's in orbit around the nucleus should emit radiation. Again, the probability of emitting electromagnetic radiation is proportional to the acceleration. So it's counterintuitive. I mean, it goes against the very same idea that we had to use in order to look for quantized states of the electrons in an orbit around the nucleus. But nevertheless, we have to have spontaneous emission as well. If we don't, then by detailed balance, we don't reach equilibrium. So we know that something is strange. Conventional quantum mechanics, that was almost a decade later, tells us that we can solve the hydrogen atom, we have eigenstates, the hydrogen atom does not decay because of these quantization things. But now we have to introduce again the possibility that an electron can decay from an excited state into the ground state. Where is it coming from? And the idea is what we know now. I think that the theory of quantum radiation came in the early 30s, so a few years after Schrödinger and Heisenberg came up with their equations. We know that actually, even if we don't have any photon around, there is an electromagnetic field. Just it's a quantum object now, it's a quantum field, and it is in its ground state. So first of all, you can have spontaneous emission because the electron sees, if you want, virtual excitations of this electromagnetic field which trigger the decay. And stimulated emission is also explained by the fact that when you have photons around, the electrons essentially resonate with these photons that you have around, and so the probability of emission is enhanced as the number of photons that you have around increases. But this is a different story now. So we have to go beyond conventional quantum mechanics. There was another reason why people in the early 30s started thinking about the fact that conventional quantum mechanics just doesn't cut it. And the idea is that people were beginning to deal with processes, high energy physics, particle physics, if you wish, and we knew that photons are created or absorbed. And then we also discovered that positrons can be created, electron-positron pairs can be created, and in high energy collision, the number of particles that you have is not conserved. This comes from relativity because of the famous mc square energy, rest energy. So if you have enough energy, you can create mass and vice versa. And this is a problem because you remember that we were dealing with canonical quantization of a physical system. We said we fix a Hilbert space, and we started saying that's a Hilbert space of a system which has that many particles. The number of particles had to be fixed. We have this Hilbert space of square integrable functions, for example, over 3 dimensions, R3, crossed with tensor crossed with the spin states, if you wish, but that was a one particle space. Okay, if we want to deal with n particles, we can define the tensor product of many one particle Hilbert spaces. But no matter how many I consider, that number is fixed. So, excuse me, there is no way that I can describe a system in which the number of electrons or whatever particles I'm dealing with changes in time if I stick to conventional quantum mechanics. Schrödinger equations are not relativistic, that's the other issue, but we kind of solved that before. We know that we can describe electrons with a Dirac equation. So something has to change. I have to find a way to describe a system in which the number of particles changes. When, after the theory, such a theory, which is quantum field theory, had been developed, it soon became apparent that if I have a crystal in its ground state, we've seen, for example, the electronic Hamiltonian and the ionic Hamiltonian of a crystal. We'll see actually the ionic Hamiltonian much better later on, in their ground states. The ions don't move, the electrons occupy the valence band, and that's it in a dielectric. If I increase the temperature, there will be excitations. Electrons can be excited into the conduction band. Ions can begin to move by thermal excitations, generating phonons. And if I consider these as small excitation away from the equilibrium or the ground state of the system, it became apparent that I can use exactly the same mathematical machinery that I was using to describe particles in elementary particle physics to describe these excitations that can be viewed as quasi-particles. And that's where the suffix on, like in phonon, magnon, polariton, plasmaron, and so on, comes from. You can view them as quasi-particles. So exactly the same machinery that using quantum field theory can be used in solid-state physics. I may add that there is another very interesting analogy. The time evolution of the quantum field can be converted into quantum statistical mechanics at equilibrium by converting time to temperature or inverse temperature, imaginary inverse temperature. So that's another analogy that I will not discuss here, but it's an interesting, extremely useful tool. So all the mathematics that was developed to deal with quantum field now becomes useful in a non-relativistic way when we're dealing with excitations of our crystals. So the issue now is we have to change perspective. We have to, I think from the very beginning when we start thinking of physics, we imagine a physical system as made up of particles, of dots, little dots that move around, that bump into each other, that interact with fields and so on. But particles have to be there. Now we have to change perspective completely. The starting object has to be a field. And particles will be viewed as quantum excitations of this field. And so the idea is now to describe the system in terms of fields Fields create a little bit of a complication because if we want to quantize them, we have to go to a Hamiltonian formulation of a system which has infinitely many degrees of freedom. The simplest idea of a system which so many degrees of freedom is a violin string. It's a string which is held fixed at two endpoints. It can vibrate, and the degrees of freedom are just the position of this string, which I view as a continuum. Clearly, it's made up with atoms, but there are so many atoms so close together compared to the length of the string that I can use a continuum approximation. And then if I want to deal with Hamiltonian formulation, Lagrangian or Hamiltonian formulation of the string, I have to move away from the Hamiltonian Lagrangian formulation of classical mechanics as we saw it before, but go to the equivalent Lagrangian and Hamiltonian formulations of fields. And so we will discover that in doing that, the Hamiltonian of a system, which I quantize, will show that excited states can be viewed as excitation of harmonic oscillators, which I can treat as particles. And this actually extends to two things, to two fields which have nothing to do, strictly speaking, with crystals. The Schrödinger field, which is actually the first example that we will deal with, and the electromagnetic field, which again has to be quantized in order to explain this conundrum of what happens to an excited state of the hydrogen atom. And then we'll look at the excitations of a solid, starting with plasmons, which is probably the easier one. Then we'll move to phonons, and we'll see what we get. So let's review what the plan is. So I will review the Lagrangian and Hamiltonian formulation of classical mechanics. As we did before. We did it already in first lectures, I believe, but it's good because I'll refresh it and it will make the transition to fields much easier. Then we'll go into fields, which means that what this will imply is if I have, say, a single particle in three-dimensional space, I have 3 degrees of freedom, so I can use my canonical coordinates as q sub 1, q sub 2, q sub 3, with the canonically conjugated momenta p sub 1, p sub 2, p sub 3. So I have an index I, which runs from 1 to 3. If I have n, big N, of these particles, then I will have 3n of them. Okay, we will let this index I, which runs over a countable number of integers, we'll let it go to a continuum. And that will be it. And then we'll have essentially a formulation of fields in terms of Lagrangians and Hamiltonians. We saw canonical quantization of classical mechanics for, again, a system of with finite numbers of degrees of freedom. We'll follow exactly the same procedure to quantize our fields. This is a very good way to do it, I think, because it's rigorous. It's the way quantum field theory was created. You can probably find shortcuts starting defining creation and annihilation operators in different ways, but this is the way that allows you to quantize any system you want, because you follow canonical quantization. Exactly the same reasons why canonical quantization for a system with a finite number of degrees of freedom is general. It allows you to quantize any such a system. The example that we'll see will be the first, the Schrödinger field. It's a little bit strange because this is a system of fermions, so there will be some slight differences with respect to what we will see for plasmons, for example. We will define the Hilbert space that has this property that doesn't force you to have a fixed number of particles. It will be a strange space. Mathematicians have struggled quite a bit to understand what the heck this thing was. And there are also major complications when we move from a finite number to an infinite number of degrees of freedom. Sorry, my vampire clock strikes again. And this time we have 11 beats. So we will see the difference between what happens to the Fock space for fermions and what is the difference with the Fock space for bosons. So particles which obey Fermi-Dirac statistics in this case and Bose-Einstein statistics in this case. We'll deal with the example of phonons. And then, although this is not like a Schrödinger field necessarily, it's not a elementary excitation of a solid, since we will have already digested, hopefully, the algebraic machinery to quantize these objects' fields, we'll quantize the electromagnetic field. And I will draw some conclusion about the importance, in particular, of the canonical commutation or anti-commutation rule. Oops, rules, not rails. My apology. Okay, so what I will do probably is I will review briefly what we saw already, the Hamiltonian formulation of classical mechanics, and then we'll take a break and we'll go to formulation of fields. So remember what we did. We have a system which is described by big N. In this case, it could be 3 times the number of particles that I have, whatever it is the number of degrees of freedom that I have, okay? And the Q's are the independent coordinates, canonical coordinates. Independent meaning that if I have constraints, particles living on the surface of a sphere, particle living in 2 dimensions, I will consider only the independent coordinates. I define a kinetic energy operator, which is, kinetic energy, functional of these coordinates, Q. This Q has a bold character because it represents a collection of these big N degrees of freedom. And I define the Lagrangian as a function which is the kinetic energy of the system, which is usually a homogeneous function of the square velocity, minus the potential energy, okay? And then classical mechanics can be formulated, F equal ma, can be formulated by saying that the trajectory that the system particles, the particle, if it is one particle, the system will follow, is given as a function of time, is such that it renders the integration of the Lagrangian between time 1 and time 2, time t2, and extreme points of this integral. So I take the integral, integrate over time between time t1 and t2 the Lagrangian, fixing the position and velocity of the particles at t1 and t2. Okay, the integral that I have, which is called the action, will be an extreme point, usually minimum, when I calculated integrating along the physical trajectory that the particle, the system, will follow. I think last time I gave, weeks ago, I gave an idea of how to solve this problem with variational calculus. If I have such an integral of a function y of x and I integrate over x between 2 extreme points, I can simply label all the possible trajectories y of x by a parameter lambda. So I add the parameter lambda here, and then what I want to do is, if I integrate for all of these trajectories, each labeled by lambda, the trajectory that I'm interested in will be the one for which the derivative with respect to lambda is equal to 0, which is exactly this. I want to extremize my trajectory, my action. If I do that, I can simply replace the, use the chain rule to express the derivative with respect to x and y dot, y and y dot. I integrate by parts this second term over here. Integrating by parts, I notice that the derivative of my unknown function y as a function of lambda has to vanish at x1 and x2 at the extreme points, because I ask for the trajectory to have fixed endpoints. And so I'm left with only this term, which I can plug it back into my integral, and I find that the derivative of this action function, this function of lambda, has to be equal to an integrand function multiplied by this. But since the way I label this function is arbitrary, this can be anything, this implies that this term inside the bracket, the parenthesis here, has to be 0. And this is the Euler equation for my system. Okay, so this defines the Euler-Lagrange equation when I apply it to my system. So going back to what I had, I go very fast because we did it already. Having defined my Lagrangian, fixing the Q to be an extreme point between T1 and T2, the solution of the problem, which is the trajectory that the system will follow, go from T1 to T2, will be a trajectory which obeys this differential equation. I go to, from considering this, which is essentially, since the Q dot is the derivative with respect to time, this is sort of a second order differential equation. So I have a system of n, where n is the number of degrees of freedom of the system, second order differential equation, and I convert it into a system of 2n first order differential equation by introducing new independent variables, which are just the derivative of the Lagrangian with respect to the Q dot. And I define these as the momenta which are canonically conjugated to the variable Q sub I. So if Q sub 1 is x, this will be just the momentum with respect to x, the x component of the momentum. If Q is a azimuthal angle in a problem with cylindrical symmetry, this will be just the angular momentum along the component of the angular momentum along Z. The idea why this was done, I remind you, is that if you look at this equation, if this is a constant of motion, or if I can find a symmetry of the problem, I said before, for example, if this is cylindrical symmetry, excuse me, the Hamiltonian, or the Lagrangian, sorry, will not depend on the angle phi, for example, the azimuthal angle, which means that immediately this is a constant of motion, because this is 0, so I find that this equation is immediately solvable. And this was done in the era when computers, of course, did not exist. Everything had to be done by hand. The main application was celestial mechanics. So going to this, I can convert the Lagrangian into Hamiltonian by introducing this new P that replaced the Q dot now as independent variable. This is called the Legendre transformation or transform, and this guarantees that this function is not a function of the Q dot anymore. And then the Lagrange Euler-Lagrange equation of motion can be rewritten in terms of the Hamilton equation of motion. So this is the procedure. From the Lagrangian, I go to the Hamiltonian by taking the Lagrangian, subtracting it from the product, the sum over all the degrees of freedom of the momenta times the canonical coordinated velocity. And this is the usual transformation that I have to follow to go from Lagrangian to Hamiltonian. We'll do exactly the same with the suitable generalization going to fields. How is it going to be generalized? By converting the sums over I to integrals over position, which will be the degrees of freedom, the label of the degrees of freedom that I have. And we will follow exactly the same procedure to derive some Hamilton equation of motion. In this case, what we do is by look at the differential of the Hamiltonian, either by simply looking at the chain rule, looking at the partial derivatives with respect to Q and P, or by looking at the differentials, looking at this expression instead, so taking the differential either this or this, and making it equal. And then we see immediately that we have this expression for the equations of motion of the system. I told you that it's kind of a curiosity, or at least first time that I saw classical mechanics in this way, I didn't quite understand what was the point, to use these Poisson brackets, which is defined as in this way. So if we have what we can call observable or physical quantities, which are functions A and B of the canonical coordinates and its canonically conjugated momenta, so the Q and the P, we can define the Poisson brackets in this way. I sum over all the degrees of freedom, the product of the derivative of the A with respect to the Q and the B with respect to P minus the opposite derivative with respect to P and B with respect to Q. And then I can write Hamilton equation in terms of the Poisson brackets. This is interesting. We saw that following canonical quantization, this will give us the Heisenberg equation of motion by replacing the Poisson brackets with 1 over IH bar, the commutator of what they become operators. And I also told you that it's quite interesting to see that we have this canonical Poisson brackets the Q and the P commute, well, the Poisson brackets gives me a delta ij, so Qi and Pj is always 0 unless I is equal to j, and then I get 1, and the Q and the P by themselves give me 0. This will be extremely important. I mentioned it before, I didn't show you why, and that will be my goal in the next lecture, to tell you why these are extremely important. So just a reminder, what you just said, I just said, if I have a classical system described by Hamiltonian or Lagrangian formulation, from the Lagrangian I go to Hamiltonian, and then I say, okay, to the system I associate a Hilbert space. Remember, this is for a fixed number of degrees of freedom. We'll have to change that, and that's why we're going to go to second quantization. And states of the system are just associated to elements or vectors in this Hilbert space. The canonical coordinates P and Q are promoted to operators over this Hilbert space. The Poisson brackets become commutators, except for the IH bar that I have over here. And the equation of motion for operators are given just by exactly the same equation of motion that I had here for observables or physical quantities in the Hamilton formulation, but for operators now. And this is in the Heisenberg picture. If we go to the Schrödinger picture, we know that instead operators do not evolve in time, but states do. I think this time I'll stop here for about, let's say, 10 minutes, if that's okay with everyone, and we'll go to the Hamiltonian formulation of fields, and then how to quantize them, and then we'll go to one example. Okay, so I'll see you at, let's say, 20 past, 22, something like that, past.
Max, may I make an observation?
Please do.
After such a tough lecture, it's only a trivial thing. If you go to slide 14, equation A21.
Okay, slide 14. This one, no?
21. A21 slide?
Yes.
Where you have the derivative, the second derivative of the energy with respect to u twice.
Yes.
I don't understand the factor of 2 at the denominator. Am I mistaken, or is it...
No, I am mistaken.
Okay.
My apologies.
No, it's just I was surprised to see that factor of 2 at the denominator, and I was wondering if there was something hidden in it.
No, the kinetic energy is not 1/4 mv squared. You're right.
Okay.
My mistake.
That's all.
Thank you. Thank you for pointing it out.
proprio quando finirà questo master civil, si ritornerà gradualmente alla classifica normale. Fondamentale differenza con il circuito ATP è che le giocatrici non potranno mantenere il 50% dei punti. Qui, come vedete sul nostro sito, sono elencate tutte quante le fattispecie. Se un torneo si è giocato o non si è giocato l'anno scorso, se si rigiocherà quest'anno. E qui c'è proprio Ashley, lei che è il numero 1 del mondo, e che però ha faticato e non poco nel suo secondo turno. Torneremo a parlare di tutto questo più avanti, perché è già il tempo di tornare in campo. In campo ci sono Elise Mertens contro Katie Bulter, la belga, del Civil, ha vinto il primo set, con 3 secondi, questo primo set.
Ben ritrovati da Miami, siamo spostati sul campo numero 3, dove la tendenza del numero 16, la belga di Mertens, avanti 7 breaks e 4-3-1 sulla britannica Katie Bulter. Bulter avanti nel primo set, per poi subire l'ente rimonta della giocatrice belga. Alla corta, ci arriva.
All right. Are we all back? Shall we get back to our things? Are we all okay? Can I start?
Yes.
Yes, yes.
Good, good. Okay. So, where's my pointer here? I lost my pointer. So, the idea now is to go to infinitely many degrees of freedom. I will talk a little bit about the different interpretation of, I don't want to be a little bit too heavy here, but the reality that we have to take in order to understand what fields are and what particles are. I'll discuss it a little bit. Let's consider the example that I gave before, which is a violin string, okay? So we have this string, and between the peg and the bridge of the violin, it's fixed at these 2 points, and then its displacement at any point x along the length of the string is called phi, okay? It's a field. It's a function, but we call it a field. And I want to describe the motion of this string in terms of a Lagrangian and, of course, Hamiltonian formulation. So what I do is, okay, I have these phi, view them as the q sub I that I had before for my system with a finite number of degrees of freedom. So the subscript I range from 1 to n, the total number of degrees of freedom. Okay, now I replace that I with a continuous variable, x, and I want to find a function, a Lagrangian, which is a function of the coordinate, phi, of its displacement. In principle, now I can have this. I didn't have it before because the index x was a discrete set of indices. Its velocity, so to speak, which is the q dot, and then in principle it can depend explicitly on the position and on time. Might be a potential, this might be the strain that I have on the string, and time if I wish. So the idea is to use the same idea, same Lagrangian idea of defining a total Lagrangian, which is as a function of time, which is the integral over space of this Lagrangian density. Again, this is the same, this integral from 0 to d replaces the sum over the index I that I had before. So I didn't have a Lagrangian density because I didn't have a continuum of indices I, and now I do. Okay, so what I do now is apply Lagrange principle. I define the action as the integral between t1 and t2 of the Lagrangian function, exactly as I did before, except that now I have to drag along another integral over x, which is replacing, as I said, the sum over the index I. And then I have to find out what is the differential equation, the set of differential equations, if you wish, that the field phi, the displacement of the violin string, has to obey in order to satisfy this Lagrange variational principle. So to make this Lagrangian or Lagrangian density an extreme point of these integrals. I can follow exactly the same derivation that I did before. I will skip the various steps, but they're exactly the same. They're more complicated because I have all this derivative with respect to space, to x, that I didn't have before. But essentially what I had is the same thing, is the derivative of the Lagrangian with respect to phi. Notice that this is a strange derivative. It's sort of a functional derivative because the Lagrangian density L, script L, is a functional of phi. Phi is a function of x and t. And then what replaces, I have an additional term that I didn't have before, the derivative with respect to x. Clearly I didn't have it because x was a discrete index. So I have this additional term, which is the functional derivative of the Lagrangian density, it's a mouthful, with respect to the derivative, special derivatives of this phi. And this comes from exactly the same procedure that I had outlined, where is it? Here, doing exactly this procedure. There is an extra step and an extra integral by part that I have to do. So this, and then there is the explicit derivative, functional derivative of Lagrange with respect to phi. So this is exactly what I had before. This was the derivative of L with respect to Q, and this is the time derivative of the L with respect to Q dot, except that now I have, in addition to the time derivative of the time derivative, I have the spatial derivative of the spatial derivative. So it's an extra complication that I have. Actually, this entire object usually is called the functional derivative of the Lagrangian. I'll describe it here. It's described over here. Okay. So the Euler-Lagrange equations for my field now become this, and if I have several fields, now I can add even an integration over an equation for each of these various fields that I have. This should be an I, not a J, sorry. Okay, to simplify the notation, but that's just a convenience, if I define this funny delta now, the functional derivative of the Lagrangian density with respect to phi as this object, then I recover exactly the same form that I had in, so I lump this term rather than with the first term, I lump this middle term with this, and I call this entire object the functional derivative of L with respect to phi. And then this is what I have. Clearly, the functional derivative with respect to phi dot remains the same. So these have a formally the same expression that I have for the Euler-Lagrange equations for a system with a finite number of degrees of freedom, except that I have these functional derivatives that I have to deal with. So formally, I'm happy. Now, what I do is I do exactly the same thing that we did before. I define the canonically conjugated momentum density to the field phi I as the functional derivative of the Lagrangian density with respect to the phi dot. Remember that P sub I was the derivative of the Lagrangian with respect to the Q dot I, and similar thing over here, except that I have functional derivatives now. The Hamiltonian is now defined in terms of a Hamiltonian density, and the Hamiltonian density is related to the Lagrangian density exactly by the same expression that I had before, that I pointed out before. That is a sum of the PQ dot, and here I have an integral of the pi phi dot. Okay, so formally everything is the same. The only complication that I have is that derivatives become functional derivatives, and that I have to drag along densities because I have a continuum of indices. In this expression, I've actually assumed that this is in three-dimensional space. To stick to the example that I had of the violin string, this would be just dx. But this is the general form in which I can proceed. And I can quantize the same way now. I can first find that Hamilton equation can be obtained from the Euler-Lagrange equation, having transformed the Lagrangian density into Hamiltonian density. And then I have that the time derivative of the canonically conjugated momentum density is equal to the functional derivative of the Hamiltonian with respect to the field. And the time derivative of the field is the functional derivative of Hamiltonian with respect to the momentum density. Exactly the same expression that I had before. If you replace the delta with a d, and you replace the phi with q and the pi with p, you get exactly the Hamilton equation that I had before. Again, the k labels various possible fields that I can have. Fermions and bosons, whatever I have, a bunch of fields that I can have. Any function of the momentum density and the field density, which is an observable, can be written in terms of an integral over its own density. I use this script letters to denote the density. And then Hamilton equation can be reformulated in terms of a generalization of the Poisson brackets. The Poisson brackets, remember, was a derivative of the Poisson bracket between an observable A and B was the derivative of A with respect to the Q, derivative of B with respect to the P, minus the opposite, summed over all the possible degrees of freedom. This is replaced by an integral now, and then I sum over the possible fields. And this will give me the Poisson bracket between two observables. Okay, and I can define the Poisson bracket density, if you wish, as the Poisson bracket at a given pair of points R and R prime. What will become the canonical commutation or anti-commutation rules, which are the Poisson brackets between the field and its canonically conjugated momentum density, are just expressed here. The field for any field I and j at two different positions at the same time, these are always at the same time, are equal to 0, except when I take the Poisson brackets between phi and pi for the same field I. And this comes immediately from the definition of the Poisson bracket density. You can verify it immediately. So these are important. They will become the equal time canonical commutation rules or canonical anti-commutation rules. How do I quantize? Exactly the same way, with a little snag that I will describe later on. The little snag is the fact that when I go to infinitely many degrees of freedom, the Hilbert space that I have to deal with, it's a serious issue, it becomes an issue. We'll talk. So I follow exactly the same procedure. I have my Hamiltonian, I can define my Hamiltonian, the phi becomes an operator, the pi becomes an operator, and the Poisson brackets become commutator except for the factor IH bar, and my canonical Poisson brackets become the canonical commutation rules that I have written here. At equal time, the field and the canonically conjugated momentum density, canonically conjugated to the field, satisfy these commutation rules. Again, I will spend some time emphasizing why they are important. Just to give you an anticipation, which I already anticipated before, these set the scale. They set essentially the fact that the commutators between phi and pi is to be equal to 1 in unit of IH bar. And this will give me, for example, the displacement of an ion due to the presence of a single phonon. It gives me the potential or the electric field associated to a single photon after I quantized the electromagnetic field. Again, these are things that one can derive or calculate semi-classically, but the correct way to do it is actually to use the canonical commutation rules. We will also discuss the fact that these canonical commutation rules can become canonical anti-commutation rules if I'm dealing with fermions. The equation of motion will be exactly the equation of motion that I've written here, with this Poisson bracket replaced by 1 over h bar, the commutator. This is always a commutator, not anti-commutator. So exactly the same procedure. Please ask me questions if you wish, but the task that we will have to quantize anything will be to write everything we know in terms of fields, and in terms of electrons, we'll have to discuss it a little bit, the change of perspective that we have to employ when using second quantization. I will tell you a little bit about why second quantization is a misnomer, but that's the way it was called originally. But then everything follows exactly the same procedure that we followed for conventional quantum mechanics. Conventional means finite number of degrees of freedom for the system that I'm considering. It's just more algebraically complicated, but actually it's more complicated, it's less complicated than it seems like. I think it's actually simpler to deal with second quantization than conventional quantum mechanics in many cases. So let's start with the Schrödinger field. If there are no questions, please interrupt me anytime. So this is our good old Schrödinger equation, and we know how to interpret it. This is an operator On the left-hand side, I have the time derivative of a state, and the time derivative of a state is given by the application of this operator that I have at the right-hand side, which I call Hamiltonian, applied to the state of the system. Okay, let's forget that. We have to junk everything that we said so far. I will not interpret this as the time evolution of a state in a Hilbert space, but I will view it as a classical field. The word classical, I put it here in quotes because there is an H-bar floating around. So how can I associate Planck constant with something classical? But let's change this perspective again. So let's view this as a field, this psi, much as we consider phi and big A as the field of the potentials associated with an electromagnetic field, or E and B as the electric and magnetic field. We view it as classical field. So we view this equation as classical. And then we're going to use this Lagrangian and Hamiltonian formulation of classical fields to derive, Lagrangian and Hamiltonian, that gives us as Hamilton equation of motion, or Euler-Lagrange equation for the field, will give us this equation for the classical field. And then we'll quantize it, following canonical quantization. So notice that particles do not appear anymore. M is a parameter. Phi is a field, psi is a field. Particles so far do not appear in our picture. So the starting point of our description of any physical system is a field, in terms of field. It has been called second quantization, as I said, as a misnomer, because it seems like we're starting from a quantum equation, which is Schrödinger equation, and then which is already quantum, and then we quantize it again. Again, it's a misnomer. I think it's much better to interpret this as a classical field, an equation for a classical field, and then do conventional quantization of this field, conventional, so to speak. So what we can do, what we have to do first, is to find a Lagrangian density such that the Euler-Lagrange equation for the field psi, in which I will express, in terms of which I will express my Lagrangian density, gives me the Schrödinger equation. And indeed, you can check that this Lagrangian density, which is IH bar times the phi star times the psi dot, minus the product of the two gradients, and the dot product of the two gradients of the complex conjugate of psi and psi itself, minus the potential times this object. If I take this as a Lagrangian density and I write the Euler-Lagrange density, I get, I'm lying here, I don't quite get this equation, I get the complex conjugate of this equation. So I can take the complex conjugate of this Lagrangian density if I wish. And the Lagrangian, then the total Lagrangian will be just the integral over space, the entire space, of this Lagrangian density. So this is the Lagrangian density that gives me the Schrödinger field. So let's call it the Schrödinger Lagrangian density. Again, we are not considering relativistic versions of quantum mechanics. In principle, I could replace my Schrödinger equation with a Dirac equation and quantize Dirac equation the same way. I can view Dirac equation as an equation, a classical equation for a classical field, which happens to be a 4-vector, and do exactly the same procedure. But I think that relativistic corrections must be used only to describe the band structure and, of course, core states of some heavy elements, like gold, for example. And even in that case, usually people don't use Dirac equation, don't solve the band structure for block function in a Dirac equation, but they do just perturbation theory in terms of V over C, where V is the velocity of the electron. So you do first order corrections, and they can be quite important for the band structures and heavy elements, heavy crystals. Okay, any question about this? I realize that this has a profound implication on how we view a physical system. So far, from what I said, it's not clear where particles are. I'm talking about the Schrödinger field as a classical field. I'm writing a Lagrangian density for this field, and I'm showing that this Lagrangian density actually, if integrated over time, gives me an action, and the trajectory, so to speak, of the field, or the time evolution of the field in time and evolution distribution in space, has to obey this equation in order to minimize the action, the generalized action that I have. Where particles are is not clear yet. We'll get there. So we can formulate this entire thing now in terms of a classical Hamiltonian. Again, classical because I'm not quantizing anything yet, and my field psi is a classical field. I define the functional derivative of the Lagrangian density with respect to the psi dot as the canonically conjugated momentum. If I look at the derivative of the psi dot here, I just get IH bar psi star, which is exactly what I have here. There's nothing else which appears in the functional derivatives because the Lagrangian does not depend on the gradient of the psi with respect to this. And so I have a Hamiltonian density now, which is by definition, I have only a field, so it would be the pi psi dot minus L minus the Lagrangian density, which is this object. Okay, now we're ready. We have the Hamiltonian in terms of a field, the Schrödinger field, and the canonically conjugated momentum density of that field. And of course, a potential that I have in my Schrödinger equation here appears in my Hamiltonian. So this we may call it as a kinetic energy, so to speak, and this is a potential energy of my field. And now we can quantize it. How do we quantize it? So now we view this object, psi and pi, and so H, the Hamiltonian density, as Hermitian operators over some Hilbert space. It's a Fock space. We will discuss what it is in a while. And we require that this field, psi and pi, obeys the canonical commutation rules, which are written here. These, again, are exactly the same expression that I wrote here, okay? This expression. The equal time Poisson brackets are converted into equal time canonical commutation rules, and this is what I'm writing here, except that now I'm using psi for phi, but it's the same thing. At the same time, okay? What happens at different times, I don't know. But I require that these commutation rules are obeyed. In turn, since pi is equal to phi star here, because I haven't quantized it, it will become psi dagger. If I quantize, this is Hermitian conjugate of psi. So this gives me the h bar goes away because it's absorbed into the pi. And so I have the pi, the psi dagger gives me a delta function, and psi and psi dagger at the same time but at different positions give me 0. The Hamilton equation becomes simply psi dot is equal to this, and you recognize it as Schrödinger equation. It's exactly the original Schrödinger equation. This is the first Hamilton equation. The second equation, which is the equation for the pi, for the canonically conjugated momentum, actually is the canonically conjugated equation to 348. So I get the same thing, except for a complex conjugation or Hermitian conjugation. Okay, so I have reformulated my problem by quantizing the field psi and its canonically conjugated field pi, canonically conjugated momentum field density, and the Hamilton equation of motion are exactly the Schrödinger equation of motion for the field. Again, though, this is not a wave function, it's not a state on a Hilbert space, it is an operator that acts on some Hilbert space yet to be defined. Any question? Should I go back and re-describe the procedure? The important thing is that this equation has to be viewed as a classical equation, classical in quotes, if you wish, for a classical field psi, which I call the Schrödinger field. I think that everybody is familiar with the electric field, maybe the gravitational field. Talking about a Schrödinger field leaves people uneasy. The field itself is a concept that I think is extremely abstract. it goes back to, I think, to Faraday with these field lines. I think that the gravitational field and electric field are kind of acceptable, and we understand what they are simply because we're used to them, because we've been exposed to them for so long. Schrödinger field, it's a new concept, but yet it's the same level of abstraction. I think the electromagnetic field is equally abstract. So I'm ready to quantize the field, and we quantize it in this way, okay? So now we have to deal with understanding what is the meaning of this. Physically, what do we get? Where are particles coming from? What is this Hilbert space of states that, where are the states? So that's the next step in understanding what we're doing. I also remind you that we're dealing with a general Schrödinger field. I've not talked about spin, and that's why I'm imposing this bracket to be the commutator. I'll mention in a while that actually, if we deal with fermions, we might as well bite the bullet and consider them anti-commutators. Okay. Let's assume now that I have my Schrödinger equation. Let's go back to my original Schrödinger equation. So this is a Schrödinger equation. Let's go back to our conventional quantum mechanics for the wave function in the presence of a potential. So this equation can be solved. There is a spectrum that we have, and we have eigenstates. These are eigenfunctions. Let's call mu the index that labels these eigenstates. Clearly, mu can be discrete, can be a continuum, depending on what the potential is and what are the various eigenstates. If this is a well and states are in the well, then it can be discrete. If this is a scattering potential, I can have a mix of discrete spectrum, continuum, singly degenerate, continuum, doubly degenerate, if I have wave functions which go back and right, from left to right, and vice versa. But let's call mu this index, regardless of whether it's a continuum, it's a discrete set of indices, as degenerate or not. So let's call it mu. And this u sub mu of r, these are just the eigenfunctions of the time-independent Schrödinger equation that I have, and their time dependence will be given simply by e to the I e mu over h bar t. Okay, and let's expand my general wave function. Again, I'm sticking to the conventional quantum mechanics. My wave function will be, in general, a solution of the general equation will be a linear superposition of these states where these coefficients can evolve in time, if I'm looking at the time dependence. Okay, now let's go back to our second quantization. These are now fields. So in principle, I should put a hat over here, and I should put a hat over these C's. These coefficients become operator over a Hilbert space. And these are just C functions, complex functions. They are the same eigenfunctions that I can calculate by solving my Schrödinger equation analytically, numerically, whatever I have to do. And the momentum, which is IH bar times psi dagger, the momentum density is given by the same expression where these C's now are psi daggers, and I take the complex conjugate of the U. Again, U are C functions, complex valued functions, and the C, I view them as operator in my expansions. Now, and this is an exercise that I don't know if I posted already a homework assignment, I will give it. If I plug these expressions into my expression for the Hamiltonian densities, okay? Remember that IH bar gradient pi is equal to grad of psi dagger, and this will become IH bar psi dagger because of this relation between pi and psi dagger. I can use the orthogonality of these U's. Remember, these are mathematically eigenfunctions of a Hermitian eigenvalue problem. So for mu and mu prime different, these will be orthogonal. I can use the orthogonality, and I will find that the Hamiltonian, the total Hamiltonian integrated over space, and that's where the orthogonality comes from, is just the E mu, which are the eigenvalues of these states that I had from my conventional quantum mechanics, times the product of C dagger C, summed over all the possible mu's. And this canonical commutation rules implies that C and C dagger commute in this way. They give me 0, so they commute whenever mu and mu prime are different. When mu is equal to mu prime, they give me 1. The IH bar has disappeared because of the definition that I have of the Psi dagger. I'm lying, and that's where things get a little bit tricky. I'm lying because actually this, if you do this, you actually end up with this expression. There is a 1/2. Actually, the 1/2 should be, the E mu should be inside the parentheses here. My apologies. Let me write it down. Let's see if I can. Pointer option, where is it? Sorry about that. Okay, so misplaced parenthesis. Okay. Oops, no. Oh boy, my poor eyesight. So you get that the Hamiltonian is the sum over all possible eigenstates of the conventional Schrödinger problem that multiplies this product of the C dagger times C, where these are these operators that are essentially the coefficients of my expansion of the field. And then there is this 1/2 term added up. To fix the ideas, if the potential is 0, these are just plane waves, e to the ik r. So mu is a set of 3 indices, indeed if we're in 3 dimensions, this index mu actually is a set of 3 indices, 1 per degree of freedom that I have in my system. So this will be just the k vector. So the Hamiltonian is just the sum over k vector of h bar squared k squared over 2m, which is the kinetic energy of an electron in free space, multiplied by this product, C dagger k ck, plus this 1/2. The 1/2 is an issue, right? Because I'm summing over all possible k's. If I use infinite volume normalization, that's a continuum. An integral becomes an integral over k over the entire k space of 1/2, which is infinity. And so typically one says, well, it's a constant, so I take it out and I measure energy with respect to this object. I think I can say now why this happens. There is, I think I'll describe it in another slide. Anyway, we'll get to that, but I'll say it now. The problem is the following. We saw in conventional quantum mechanics that the Schrödinger representation and the Heisenberg representations are equivalent. Actually, the Hilbert space that the Hilbert spaces that they apply to are different. But there is a general property, a general theorem actually, that says that if you have a physical systems with a finite number of degrees of freedom, any representation that you use is isomorphic to any other one. In other words, they're all equivalent. The Hilbert space is the same. You may represent it in terms of matrices, operators in terms of matrices, as Heisenberg did. You may, which is essentially a matrix, which may be a continuum matrix if the spectrum is continuum. You may represent it as differential operators, as Schrödinger did. But the representations are equivalent. The interaction picture is also equivalent, in which you do a mix. The problem is that if you go to a system with an infinite number of degrees of freedom, this is not true anymore. And that's a major nightmare. So you never know what is the proper Hilbert space which is associated with the system. So the rule now is more complicated. You cannot say, I have a system associate some Hilbert space to the system. No. If you have a system which is given by your field with an interaction among the fields, the Hilbert space changes as the interaction term changes. And this is a big issue, and it causes what is known as the renormalization issue. Anything you write is infinity, because you always use a Hilbert space which is the wrong one, which is not the correct one. So this is, if you want, is a benign term that you have. By the way, if you remember, I will describe it in a minute, but if you remember the algebraic solution of the harmonic oscillator in quantum mechanics, consider just a fixed mu, so take only one mu, get rid of the sum. You realize that this is a Hamiltonian harmonic oscillator, where these are the raising and the lowering ladder operators. I'll re-describe it in a minute. And this is just the energy of the ground state. So this can be viewed as the collection of infinitely many harmonic oscillators for electrons which are in free space, no potential. This will be just the k vector, so plane waves. So this is a collection of harmonic oscillator. Each harmonic oscillator represents an electron with a given k vector. In its ground state, the energy of the system is just the sum of the energy of the systems of all the ground states of the harmonic oscillators. And I can excite each harmonic oscillator, and that's where particles come from. They're excited state of each of these harmonic oscillators that I have here. So we started from a field, we quantized the field in such a way, defining a Lagrangian and a Hamiltonian first densities and then operator density on some Hilbert space, and particles arise as excitations of the field up from its ground state. In its ground state, it's a collection of harmonic oscillator, each corresponding to one particular electronic state, and the energy is infinity simply because each harmonic oscillator has this 1/2 h bar omega, if you wish, which is this object, and the excited states are electrons which are excited into each of these quantum numbers, k vectors, if there is no potential. So the idea is how to renormalize this mess is to simply ignore this 1/2 and say, okay, the energy of the ground state is infinity, but it's a benign infinity. It's just the ground state of all of the harmonic oscillators. And I can measure any energy of any excited state above the ground state as the difference from the energy of the ground state. It's more subtle than that, but for now, let's say that you will just ignore this 1/2. The problem, as I said, is more serious than that. We can view this in a different way. If I define the variable q sub mu and p sub mu, this is sort of a generalized canonical coordinate of harmonic oscillator mu, and this is canonically conjugated momentum mu, momentum p to the state mu. If I define it like this is simply algebraic manipulation. I can rewrite this Hamiltonian, which is the Hamiltonian of these particles, which are exact solution of my problem in the presence of a potential, as this way. It is just the Hamiltonian of a harmonic oscillator, the 1/2 p mu square plus the 1/2 q square. This is just the Hamiltonian of a harmonic oscillator. And then I'm subtracting out the energy of the ground state when I take away the 1/2 that I have over here, okay, which is 1/2 e mu. Any questions so far? So this is the major thing. I think the most important concept that we have now is this idea. Oops, my apologies, now it's noon. Okay, I guess we're done. No, one more? Okay, sorry about that. So the main idea is the field, start from scratch. The field is given by a classical equation, or an equation that I interpret as an equation, a field equation for a classical field. I find a Lagrangian or a Hamiltonian, or Lagrangian and Hamiltonian densities, such that the Hamilton or Euler-Lagrange equation for these densities give me the equation that I want, that I start from. So the same equation. Having done that, I proceed to second quantize it. Again, second quantization is a misnomer, by promoting the field and all functions or functionals of this field and densities as operators over some Hilbert space. Having done that, I take the field, I expand it into, in this particular case, as, let's view it as single electron states of my conventional problem, the eigenstate of this Hermitian eigenvalue problem. I expand it in terms of these coefficients. These coefficients are promoted to operators when I promote fields to operators over this Hilbert space. And then The Hamiltonian can be viewed as a collection of harmonic oscillators, each of them representing one electronic state. The system, the ground state of the system, is equivalent, it corresponds to a state in which all harmonic oscillators are in the ground state, and I take this energy out, and I consider it the zero of my reference energy. And then excitations, excited states of the system are just states that correspond to one or many harmonic oscillators being in a first excited state. If these are bosons, you realize that this is a harmonic oscillator. I can generate as many excited states as I want, energy 1, 2, so on, which corresponds to generating 1, 2, 3, n particles in each harmonic oscillators. If these are fermions, I cannot do that, and that's where we will come and impose that actually these fields satisfy canonically anti-commutation rules, as I will show in a minute. I hope it's clear. It's a complete change of mental attitude here. Rather than starting from a particle and then looking at the equation that the wave function associated with that particle has to satisfy, I start from a field equation, and then I look at a particle as an excited state of the quantized field that obeys that particular field equation. So completely different. You see that we have achieved, although I've not described Fock space, we have achieved the main task or solved the main problem that we had. I'm not restricted to a finite fixed number of particles, as large as I want, but fixed. Now I can have as many particles as I want. All harmonic oscillators may be in a ground state. An arbitrary number of them, and there are infinitely many of them, can be excited into the first, second, third excited state if I'm dealing with bosons. So I can have as many particles as I wish. There is no particle number conservation that I have to obey in general, in principle. Now the particular Hamiltonian that I have may impose that, but in principle I don't have that. This is extremely useful when treating elementary excitation in a solid. I can absorb a phonon, I can emit a phonon, so I can decrease the number of phonons by -1 or +1. I can excite electron hole pairs. Usually fermions, okay, I don't want to go into lepton number conservations, but fermion number usually is conserved if I define it as number of fermions minus number of antifermions. So if I define an electron as a fermion and a hole as its antiparticle, then I can always generate an electron hole pair by light, thermally, whatever. So the fermion number is not conserved necessarily. I can change it by pair. But the number of particles is not fixed anymore. It can be varied. So excitations of a crystal above its ground state can be described with a machinery which is very similar to this one, and I will use plasmons as a first example before dealing with phonons. I'm not sure we'll finish today, but as an example on how to proceed. Good. Let me remind you the issue of the harmonic oscillator in case you have forgotten. Dirac found a way, very elegant, to deal with quantum harmonic oscillator. This is conventional quantum mechanics 101 if you wish, without having to deal with Hermite polynomials and fancy stuff like that. So the Hamiltonian harmonic oscillator can be written this way. M is the mass of the particle, P is its momentum, so this is just the kinetic energy, and the potential is a parabolic potential where this big K is the spring constant, if you wish, the strength of the force. Force will be minus kx, away from equilibrium position, which is at x equals 0. So Dirac defined some operators. If we quantize it, P becomes an operator and X becomes the multiplication operator, position operator. So he defined two operators, A plus or minus, which are defined this way. They're a linear combination of P and X, with these coefficients. Okay, these coefficients are, if you wish, they're the square roots of the coefficients that I have in front of the P square and the X square over here. And here I have an I, so that if I write A plus A minus, I get exactly the Hamiltonian, which is what I wrote here, except for the fact that since P and X have to commute, this is the canonical commutation rule for a particle in one dimension, the Hamiltonian can be written as either a plus or minus plus 1/2 h bar omega, where h bar omega is just the square root of k over m, the usual frequency, the classical frequency of the harmonic oscillator, or I can swap the plus and the minus, and I get an h bar omega with a minus sign in front, because of these commutation rules. This can be verified immediately from these expressions. Sometimes it's a plus and a minus, and actually that's the way I defined it before in the fields. They are divided by square root of h bar omega, so that the commutation rules between a plus and a minus is equal to 1. But for now, let's define it this way. You're free to divide it by square root h bar omega if you wish, the expression for a plus minus. Now, the interesting thing is the commutator of the Hamiltonian with a plus or a minus is just h bar omega times the same operator with a plus for a plus and a minus for a minus. And this follows directly from the canonical commutation rules and the definition of the A's. This is interesting because let's consider the fact that we have a ground state. The potential is a minimum because it's a parabolic potential, so there must be a minimum energy. Let's call H0, E0, the ground state energy, and with a bracket notation, 0 is the ground state of the system. Using this commutation rule, we find immediately that if I consider the state A plus applied to the ground state, the commutation rule tells me that this will be exactly equal A0 plus h bar omega. So what I have is that if I look at this equation as an eigenvalue problem for the state A plus 0, the eigenvalue A plus 0 will be E0 plus h bar omega. And I can keep doing this. If I now consider the state A plus applied to 0, I will get a 2 over here. So I can generate the entire set of eigenpairs, of eigenvalues and eigenvectors of my Hamiltonian by applying repeatedly the operator A plus. And this operator is called the ladder operator. It's like climbing a ladder. And this is the operator which makes the climb up one step. So it's called the raising operator. It raises the eigenvalue by 1. Vice versa, if I look at the action of the operator A minus on the state 0, I see immediately that it doesn't exist because it lowers the energy by an amount h bar omega. But since we have assumed that this is the ground state, there can be no state which has an eigenvalue which is less than E0, which means that this state A0 is equal to 0. And this implies automatically that E0 is equal to 1/2 h bar omega. So excited states of the harmonic oscillator are generated by applying n times the operator, the raising operator A plus, and they correspond to eigenvalue, which are n plus the 1/2, the ground state energy that I have. Notice that the Hamiltonian can be written, as I wrote somewhere here, as A plus 1/2 h bar omega. Let's go back here. Notice that this is C dagger C plus 1/2, and this plays the role of h bar omega. And this is indeed why this can be viewed as a collection. Each mu is a harmonic oscillator, an entire Hamiltonian is a collection of harmonic oscillators. And their ground states will be the ground state of each harmonic oscillator, and excited states will be obtained by applying to the ground state the operator C dagger. What is, okay, before doing that, let me go back to what I had anticipated before. So far we have talked about a Schrödinger field, no spin, no nothing. We know, however, that eventually we'll have to introduce spin. The spin statistics theorem is a well-known theorem. Its proof is quite simple or trivial. There is an entire book by Streeter and Whiteman called PCT, Spin Statistics and all that. in this booklet, it's not very thick, but it's not easy reading, to say the least. They show that actually particles which have half-integer spin must be associated or might be elementary excitation of a field that obeys the canonical anti-commutation rules. And on the contrary, particles which have integer spin must be associated or must be elementary excitation of fields which obey the canonical commutation rules. This comes from a bunch of axioms, which are relativistic invariance, causality, locality, and blah, 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 which are called the Whiteman axioms of any quantum field theory, relativistic quantum field theory. So it's a complicated beast. I might have given a rough idea in the past of rough and wrong, but it's suggestive of why this must be so. You need to have a wave function of a two-particle wave function for fermions that has to be antisymmetric under a swapping permutation of the two indices. So if I swap electron 1, electron 2, the wave function must be equal to minus the wave function of before I swap the two electrons. And that's because rotation associated with the operator of e to the I, the angular momentum times the angular momentum in units of h bar, spin is 1/2, or any half integer value of angular momentum. You need to rotate by 720 degrees to go back to where you started from, which in turns means if I rotate my wave function to particles by 180 degrees, which is equivalent to rotating the system by pi, which is equivalent to swapping particles 1 and 2, I get a minus sign in the term for the rotation that I have done to the two-particle wave function. So it's a complicated story, but it's a main reason why particles of half-integer spin have to obey Fermi-Dirac statistics, and particles with integer spin have to obey Bose, let's call it Bose-Einstein statistics. Actually, Bose derived the whole thing. I think he couldn't publish it. And if I know my history right, Einstein is the person who convinced the editor of the journal to publish it. And that's why it's called Bose-Einstein. But the entire thing was done by Bose. Anyway, so we might as well start by saying that if I have anti-commutation rules, so I replace these canonical commutation rules, where are they? Somewhere here. Instead of commutators, I use anti-commutators. So instead of phi pi minus pi phi, the anti-commutator will be phi pi plus pi phi. Labeled here as a minus here to indicate that this is the commutator, and a plus if it's the anti-commutator. We will see that indeed we get what we wanted. Pauli's exclusion principle, the antisymmetrization of the wave function, and so Fermi-Dirac statistics for half-integer particles. So what is the space, this famous Hilbert space that we're dealing with our system of as many electrons as we wish? Well, let's consider the absence of a potential. So flat potential, my states mu are actually states k, labeled by a k vector. They're plane waves. The vacuum state is this ground state 0, and a wave function for a state or a state in which a single harmonic oscillator labeled by the quantum number k, the wave vector, is excited, is obtained by taking the ground state of my system, my many electron system, applying the raising operator for this particular harmonic oscillator, C dagger, and this is the state which ascribes one electron in the excited state k. And the wave function will be just a plane wave, normalized to the infinite volume normalization. This is the usual thing that we saw in quantum mechanics 101 for an electron in 3 dimensions, free space in 3 dimensions. So let's call k in the ket notation for this particular ket, this particular state. So again, C dagger times applied to the ground state gives me this state. So this is the state in which a single electron is excited. Notice also that applying C to the state K, because of the property that we showed here, here, gives me the ground state. So this C dagger is called the creation operator. Remember, this is the, if you wish, the Fourier coefficient of the field, or the coefficient when I expand my field into the C functions, which are the eigenfunctions of the Schrödinger equation, considered classically, okay? And C, the operator C is called the annihilation operator because it destroys a state K. You see that I can immediately generalize it. If these were bosons, so if these were harmonic oscillator, I can create many electrons into a state K, and I can destroy one electron in a state in which I have more than one electron K. Here, however, I will consider the case in which I have anti-commutation rules. We'll see immediately that I get the Pauli exclusion principle. The idea is that the C and C dagger anti-commute. The C daggers anti-commute among themselves. And this is the crucial step. First of all, we know already that C dagger C gives me the ground state, cannot exist. So the C dagger K, applied to the ground state gives me 0. 0 means the state does not exist. It's an annihilation operator which tries to bring a state below its ground state, which doesn't exist. The state instead in which I apply this operator onto the single electron K, the state CKK gives me 0, the ground state. I should say ground state, not 0. If I apply again to the ground state the creation operator K, I get back K. So you see that the operator C dagger KK gives me 0 when I have no electrons in my system, gives me 1 as an eigenvalue when I have 1 electron in state K in my system. So we can view as the operator C dagger KK as a number operator. It's an operator that counts how many electrons I have in a particular state K. And indeed, the Hamiltonian can be written as the sum over K of the number operators for its harmonic oscillator. Notice that, and that's the important part, this is where Pauli's exclusion principle comes from. Suppose that I consider the state in which I have 1 electron in a K state, which means that I have taken the ground state and I've applied a C dagger. If I apply C dagger to this state, so I try and put another electron in a state K, because of the fact that the C dagger KCK, this guy, anti-commute, C dagger K is equal to minus C dagger K, which means has to be equal to 0. Or vice versa, that this state is to be equal to its opposite, which means that it is 0, which means that a state that I would like to obtain in which I have 2 electrons in a state K does not exist. So this is Pauli's principle, which I obtained directly from the canonical anti-commutation rules. And by the way, if I consider, I think I have it somewhere here, let me do it here. If I consider the state in which I take 1 electron in state K and then I create also 1 electron in state K prime, the anti-commutation rules of these 2 operators imply that the wave function that I have is anti-symmetric if I swap the electron with state K prime with the state of electron K. So I also get the anti-symmetrization of the wave function automatically. So what is the set of states that I have? The set of states that I have, by the way, this is just what I said before, the Hamiltonian actually can be shown that the state K is actually an eigenstate of the Hamiltonian with energy Ek, obviously from these considerations. So the general state that I have, that I can create on this Hilbert space, is I start from the ground state, and then I apply the creation operators for various states, 1, 2, and these may label the various K vectors that I have for the electrons, n times each. And n can be either 0 or 1 if I'm talking about fermions. For bosons, of course, it may be as many as I wish. So I can have as many states in which any state that I want to consider as my Hilbert space is a state in which some harmonic oscillators, some electrons in a state, in some state Ki is excited and some in which they're not. So any possible combination of electrons filling or not filling all the K states that I have. And I will call such a state as N1, N2, N sub N, blah, 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 where I simply label with 1 the harmonic oscillators that are excited in a first excited state. And their energy will be just N1 E1 plus N2 E2 and so on, which is what we saw before. Okay, what is this funny state space that I've built? This Hilbert space that I'm building I start from a single particle Hilbert space. This may be just the Hilbert space of square interval function over R3. I can add spin if I wish, in which case I can put 2 electrons in Hilbert space because I think I skipped this slide, but if I add spin, I have to add an index to my creation and annihilation operators because my field will have 2 components. So these are the Fourier coefficients of two vectors that I have, a spinner. And these are the canonical anti-commutation rules that I obey. So this means that I can actually put 2 electrons in a given state, provided the spins are different, because then I have a 1 over here. Okay. So I start from this Hilbert space of a 1 particle, L2 over 3 vector of tensor product SU2, which is the space of rotation in 2 dimensions, if you wish. Then I consider the space that I had by taking the outer product or the tensor product of 2 such Hilbert spaces. This will be a 1 particle Hilbert space. This will be a 2 particle Hilbert spaces, and I add them. Then I do this thing, this tensor product with 3 Hilbert spaces of 1 particle. So I get a Hilbert space for 3 particles, and I add it, another addition of these Hilbert spaces, and I keep going forever. So this is the Hilbert space that comprises all Hilbert spaces for as many particles as I wish. So it's a product up to a finite number of particles, but then I add for all possible number of particles up to infinity. It's a complicated object. Frankly, I don't know if there is a rigorous or a definition of Fock space that a mathematician expert in functional analysis and topological vector spaces would consider rigorous. But anyway, this is something that physicists a little bit cowboy style have been dealing with. Again, this is something that I think I mentioned before. Fock space is actually the Hilbert space which is associated with non-interacting particles. There is this sad theorem, which is called Hag theorem, that says that Fock space can describe particles only if they non-interact, or if you wish that if I use the interaction picture, I can only deal with non-interacting particles, which is kind of a non-starter, right? And this theorem implies that if I want to solve any problem that I wish in a system of second quantized interacting particles, anything I will write will diverge. Any integral will be infinity. So there is the usual normalization issue. And that's what Tomonaga, Schwinger, and Feynman did in immediate post-war years when they found a way to renormalize quantum electrodynamics and get finite numbers out of their calculations. The correct way to do it, well, I'm not implying that it's not correct, but a formal proof that what Tomonaga, Schwinger, and Feynman did was correct, it came from constructive field theory, which is building for a given interaction, building the proper Hilbert space, which is associated with that interaction, which is not isomorphic to the Hilbert spaces associated with other interactions. So I'm not going to spend any more time on this, but it's the ultimate cause of the infinities that we see whenever we deal with quantum field theory and also elementary excitation in solids. It's the same thing, because we have many bodies, which means that we're dealing with a space which can deal with a number of particles which is as large as we wish. Okay. The first example that I want to deal about how to quantize a field which is not the Schrödinger field. So let me go back here. Remember what we did. We started from an equation for the field. We thought of it as a classical equation for a classical field. We looked at the Lagrangian and the Hamiltonian for that particular case or that particular field, such that the Euler-Lagrange or Hamilton equation give me the starting equation, which is my classical Schrödinger equation, and then we quantize it. This is not always what we will do. Sometimes, to deal with a system which is given with described by infinitely many degrees of freedom, we will actually start from the Hamiltonian itself, or the Lagrangian itself, by expressing the kinetic energy in terms of the canonical variables or canonical fields that we have, and the potential energy. And that's what we'll do to deal with both electrons and both plasmons and phonons, for example. So let's deal with plasmons. I hope you remember what plasmons are. I have an idealized situation in which I have an electron gas, bunch of electrons. They are embedded in a gellium of positive charges, which typically may correspond to the dopants that you have in the doped semiconductors, to the ions that you may have in an ion plasma. If I move a little bit of this, so the ground state is a system in which the electrons and the ions occupy the same region of space with a uniform density, so everything is charge neutral. But then if I change the density of the electrons locally by increasing it or decreasing it a little bit, then I will have a region in which I have positive charges where I've removed electrons, and the electrons which are surrounding this positive charge will try to go back to where they were taken away from because of the positive field, the attractive field that they see towards the positive charge. And they will move back in time. They will overshoot the positive charge and come back. I gave you the example of the slab in which I have a flat slab of gellium electrons. I move the electrons a little bit and they oscillate back and forth with a given plasma frequency. So we want to quantize this thing. It's probably the simplest system that deals with an elementary excitation of a crystal. So let's look at this continuum model, this continuum approximation, and let's describe the Lagrangian density in terms of the displacement of the electron from their equilibrium position. So grad U is actually the divergence of the charge, and phi, which is the electrostatic potential. Let's assume that everything moves slowly enough in time so that I can ignore retardation effect and I solve only Poisson equation instead of having to solve the full set of Maxwell's equations. So the kinetic energy will be just 1/2 the electron density times the mass of the electron times the square of the velocity. And the potential energy will be just 1/2, because I want to avoid the self-energy, the change of the charge due at a given position due to the fact that I've moved away the electrons from the charge, times the electrostatic potential, which is due to this charge itself. Again, in En, the product of the charge time n is equal to rho, which is the uniform charge density. We can call it rho sub 0. Okay, good. Now, the displacement delta rho, of the charge, the delta charge that I have is related to the displacement taking its divergence, right? If I have a uniform displacement, I get nothing. All electrons are shifted by the same amount, same way, and I don't have any charge. So I have to have a divergence of the displacement in order to expose the charge. So the charge that I have, the delta rho, will be given by rho times minus the divergence of the field, the uniform charge density in the denominator here. On the other hand, the potential that I have here can be obtained by Poisson equation. This is clearly given by the minus the charge. I'm assuming they're electrons, so the minus goes away, and divided by the electric constant of the medium. I'm assuming this continuum approximation. And this is simply given by using this equation of 381. I can replace delta rho with the rho times the that minus the divergence of the field. So these are the basic equations that control my Lagrangian, and these are, if you want, they're the equations that I want to derive as Hamilton equation of motion. Before doing that, I take Fourier transforms. So I expand the potential and the displacement in terms of their Fourier components and plane waves, okay? So if I go back and look at what is this Poisson equation, I get simply the famous Q square that I have. This is just the Laplacian, okay? And so now I can use all of this mumbo jumbo over here to express the kinetic energy and eventually the potential energy as an integral over R, over space. And the idea is that I want to find a Lagrangian density, if you wish, or express it in terms of Qs, or harmonic oscillators eventually. So the kinetic energy can be written just by the U dot of the displacement, the velocities. This is the Fourier component of the velocity, multiplied by the charge, the electron density, if you wish, mass density. The potential can be expressed the same way by using this expression for the Poisson equation, and I find that the potential energy is a sum over the square of the U's. So notice that I have something very nice. The kinetic energy is given by some prefactor times the sum over Q of the square velocities, and the potential energy is some prefactor, both of them have 1/2 in front, of the square of the potential, of the displacement, sorry. So I hint here, or I smell harmonic oscillators, the square of the velocity, the square of the displacement, which is essentially what the Hamiltonian harmonic oscillator is. So the total Lagrangian, which is the difference between kinetic energy and potential energy, is given by this expression. I can now write the Hamiltonian by doing the same canonical procedure to find out what my Hamiltonian, the canonically conjugated momentum density is, and I can write the Hamiltonian instead of going through the density. I've already expressed it in terms of Fourier components, and it will be the square of the momentum plus the square of the position, exactly what I want for a harmonic oscillator. And there is this factor over here. If I actually divide it by m, I get the square of the plasma frequency. So we're in good shape. We already see that it's going to be very easy to write the Hamiltonian of my plasma in terms of a collection of harmonic oscillators. The important thing will be now to write it in terms of creation and annihilation operators that obey the canonical commutation rules now, CCR, commutators, because plasmas do not have spin. So what do I do? Okay, I know that this can be interpreted as canonical fields or canonical coordinates. They have to obey the canonical commutation rules for any Q, the same way the C and C daggers for my electrons, same expression that they had to obey. So I define some momentum P and canonical coordinate big Q by essentially normalizing it so that I get just a factor of 1/2 over here. I've absorbed the square root of NM and the square root of this object into the definition of this big P and big Q, so that I have essentially the Hamiltonian of a renormalized, normalized, I should say, harmonic oscillator, rescaled. That's the correct term, rescaled harmonic oscillator variables. Okay, now, and that's a trick that we will be using constantly, I define some operators B and B daggers in this way. You can invert it and see how B and B dagger become expressions, functions of P and Q and P and their daggers, okay? Having introduced this frequency, which we recognize is the same plasma frequency that we discussed at the previous previous lecture. So if I plug now back into my expression for the Hamiltonian, the expression for these objects that now become operators, because I've implied that I've asked that they satisfy the canonical commutation rules, you can write the Hamiltonian, this Hamiltonian, in terms of the operators B's in this form. But the B and B daggers commute. And so I can actually rewrite my Hamiltonian as the B dagger B multiplied by the plasma frequency, plasma energy. In principle, it should be inside the bracket, but since this does not depend on Q, I can take it out of the sum. And then there is the usual 1/2, which is coming from the canonical commutation rules of the operators, which is something that we will ignore dutifully. So we will jump from this equation to this expression, removing the 1/2. Taking, as we did for the electrons, the ground state energy of the system as the reference energy, even though it is infinite. A correct way to do it maybe would be to use finite volume normalization, so that this sound is finite, this number is as big as you wish, but it's finite. Consider it as the ground state energy and the reference energy, and remove it and reference all energy to this value. The U and the phi, the displacement and the potential, can now be their operators, because we have expressed everything as operators over my Fock space for bosons now. They are functions of the creation and annihilation operators of the plasmons. So notice again that the Hamiltonian is a collection of harmonic oscillator. As for electrons, we had the C dagger K, CK for free electrons. Now we have Q, which plays the role of K, is the wave vector of the plasma waves. And we can see that the Hamiltonian is a collection of plasma oscillators, harmonic oscillators. And the H bar omega P in this approximation is a constant. If you do things a little bit better, there is a small term which gives a group velocity for plasmons, an acoustic component if you wish, but then we can bring it inside the sum if you wish. So exactly the same form as we had for the electrons, except that now these B's and B daggers obey canonical commutation rules rather than anti-commutation rules. What is the Fock space for these objects now? It's slightly different than the Fock space for electrons, because I can generate as many excitations as I wish for each harmonic oscillators. So the given element in Fock space will be in principle given by a state like this, in which I take the harmonic oscillator Q1, I simply wrote it as 1 here, which is a plasmon with a vector Q1. I apply N1 times the creation operator of B dagger, which means that I create N1 plasmons with that particular wave vector Q1. I do the same thing at another Q vector Q2 and so on, an arbitrary number as many as I wish. So this will be an eigenstate of the Hamiltonian. It's actually not normalized. If you remember, for the harmonic oscillator, the excited state n had to be normalized by 1 over the square root of n factorial. So we have to do the same thing here. Every time I apply nu1 times a creation operator, I have to divide by the square root of n factorial. This is actually crucial. This is the ultimate reason why we have the Einstein's coefficients. You remember that we started talking about canonic second quantization by saying what happens to the hydrogen atom, which is an excited state. It has spontaneous emission and it has stimulated emission. And this is exactly where it's coming from the normalization of these eigenstates. So this is what will give us a rigorous justification of the Einstein's coefficient, independent from the detailed balance considerations and statistical mechanics that Einstein employed. Let's do a calculation that uses these guys, for example. It's interesting because it also implies that these canonical commutation rules that we have here, this B dagger and B commute and obey exactly these commutation rules That's why there is actually this normalization factor here. They give me 1. This is actually what fixes everything, fixes the scale of the potential. Let's see where it's coming from. And I think I'll stop here for today, having done this simple derivation and having made a comment about a semi-classical argument that one can use, one can exploit to obtain the same result. So let's assume that I want to know what is the potential, electrostatic potential, which is associated with one plasmon. We can do exactly the same calculation with photons for the electromagnetic field associated with one photon, as I said, and we can do the same thing for the displacement of an ion due to one phonon. So exactly the same procedure. So plasmons are bosons, so they obey the Bose-Einstein statistics, and this is the number of plasmons of momentum Q, so energy h bar omega Q, which actually does not depend on Q, but this is the general expression. That tells me what is their occupation number at the given non-zero temperature T, and Kb is Boltzmann constant. So what I want to do is calculate the expectation value of the square potential on a state in which I have a given number of plasmons with momentum Q. So the calculation of the expectation value will be relatively simple because I have to calculate the expectation value of B dagger and B on states of this sort. And you realize that I can, if I have an extra B dagger Q here, I can move it, or B here, let's take a B, I can move this B across the B daggers n sub n times, and the idea is to bring this BQ operator facing the 0. This will give me a 0, and that's why I'm doing it, because it will be an annihilation operator of a plasmon on the ground state, which gives me 0. But I'll be left with the leftovers of the commutation that I have to do in order to swap the B with a B dagger. With a B dagger, if I use the expectation value on the transpose of this state, I will have to consider the B dagger, which has to be commuted with many B's that I have from the emission of this guy. So the calculation is relatively simple, and actually it's the way you do it in order to show that the Fock space state for bosons has to be normalized by the square root of the n factorial. You get the n factorial. So if I want to calculate the expectation value, the potential, for a given plasmon of momentum Q on a state in which I have a number n of Q of these plasmons, what I do is I take this expression, take its product with the complex conjugate, I get the square of that stuff that I had over here. Oops, where am I? Here. I get 1 over Q squared times this object without the square root. The minus goes away. So I have this guy, and then I have the expectation value of the BQ times NQ, which is this state. It's not dagger because it's acting on the left. This is acting on a ground state on the right. The B dagger. So this is this state. And this guy is this state. And in between, I have the product of the phi dagger, which is B plus B dagger, and the phi, which is B dagger plus B. I do this simple thing, the simple calculation. The BQ square and the B dagger square vanish, because this will give me a state which has 2 plasmons with momentum Q on this state, and none, and those are not present in this state. So I'm only, and the same thing, the opposite thing happens with the BQ. The BQ acting on this state give me 2 extra plasmons with momentum Q on this state, which I don't have of this. These are different eigenstates corresponding to different eigenvalues of the Hermitian Hamiltonian, so they're orthogonal. So I'm only left with twice the terms, the cross terms, the BQ B dagger and B dagger BQ. I can anti-commute one of them to get a B dagger Q, and I get a factor of 1. So I have 1 plus twice the expectation number, the expectation value of the number operator, B dagger B dagger, sorry, B dagger B, which is n sub Q. So I have that the square, let's call it the mean square, the expectation value of the square potential on a state in which I have NQ plasmons is given by this expression, h bar omega p divided by 2, the electric constant Q squared. So if I take the thermal average and I say, what do I have at equilibrium? I can replace the expectation value of Q with the Bose-Einstein distribution of Q. So the big N, which I call big N, okay? This is an operator, this is a number, a function, okay? So I have that the root mean square of the potential now is just given by that. If I don't have any plasmons, the 0-point motion of a harmonic oscillator corresponding to one plasmon is given by this expression. This is actually quite interesting. If you have in mind the expression for scattering with the plasmons, it's exactly the coupling constant that you have, so to speak. If you think about scattering of electrons with longitudinal optical phonons, has exactly the same form, and we'll see where it's coming from. Now, I can use this procedure. In this case, it's relatively simple. I encourage all the students to work out this and convince themselves that indeed this is what you get. There is if I want to do it in more complicated geometries, suppose that I want to calculate plasmons in a system in which I have a quantum well with barriers and well materials, and I have many layers. I would have quite a complicated situation to deal with. There is an interesting way to derive exactly the same result, so that the amplitude of the potential is given by this expression following a semi-classical argument. And this is the following. Plasmons are eigenexcitations of the system. So they correspond to some electric field, again, and using a adiabatic approximation, so to speak, no retardation. And so I can express for each plasmon, the potential that is associated with that excitation as a term like this. I have an electric field which is given by some amplitude times a cosine. It's a wave that is propagating. So the potential would be expressed simply by the gradient of this thing, which is, the divergence of this thing, which is this. Okay. Now, these are harmonic oscillators, and for these, there is the virial theorem, if you wish, that says that the time average of the kinetic energy is equal to the time average of the potential energy. So I can consider the total energy of the system as twice the potential energy of the system. The potential energy of the system, twice times, is obtained by integrating for each mode Q and frequency omega, the charge density times the potential. This gives me the energy density, if you wish. Okay, and I can use this expression. The time average gives me just a factor of 1/2 that cancels this factor of 2, and then I have simply the dielectric constant times the amplitude of the potential. If you want, this is just the 1/2 epsilon times the square of the field. It's another way, time average, it's another way of getting it, times the normalization volume that I'm considering, okay? Epsilon s must be the epsilon infinity, the optical dielectric constant of the material, because I'm considering high frequency oscillation. Okay, now this is a classical argument. Now let's do the trick. Actually, one can show that if I consider epsilon as the dielectric function that we'll see later, the dielectric response of the electron in the plasma, at the plasma frequency, this is equal to 0. And that's because the ground state energy of the classical system corresponding to plasmon is 0. Quantum mechanically, we know that it's not. So let's do this little trick, and let's say, well, classically this is 0 because the system is in a ground state. Let's set it instead to the ground state energy of the system, 1/2 h bar omega p times the volume, normalization volume. And then we see that phi of q, which is what I get from this integration, is equal exactly to aq divided by q, okay, which is this object, which I can obtain from this expression, okay, which is exactly what I get from this equation. This is a procedure which I think I say, and there is a typo here, Ferrel has two L's. This is not Frank Stern, it's another Stern, I don't know what the first name was. This is a procedure that they use to calculate the plasmon energy losses by an electron on a thin metal foil. If you shoot electrons on a thin metal foil and you do spectroscopy of the energy losses of the electron, you see peaks, which corresponds to the plasma energy, actually, surface plasmons. But and in order to quantize the excitation, they use this trick. Actually, it works, and that's because of this argument. Sorry, because of this argument, you can really take the total dielectric function of the system, which is 0 at the longitudinal mode of a system, and we shall see, say the total energy of the system is 0 classically, but set it to 1/2 h bar omega of your excitation quantum mechanically, and it corresponds and actually can be proven rigorously to doing the canonical quantization, which in some cases it's a very complicated algebraic procedure. Okay, I'll stop here. Next time, which I think will be in 2 weeks because it's Good Friday next Friday. So in 2 weeks we'll deal with phonons and how we blah 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 will massage phonons. I'll give a simple description of a monatomic chain and a diatomic chain. We will also use to calculate the dielectric response of the crystal and how to quantize them. Okay, any questions so far? Everybody happy?
I have one.
Yes, please.
I remember that in the quantization of the electromagnetic field, you start from the classical description of the energy, and then you play a trick because there are 3 independent expressions of the square of the field, depending on putting the momentum operator to the left or to the right, okay? So you get 3 independent expressions, and then 2 of them have an energy that diverges, and the other one does not diverge. So you say, I like this one. Is there anything that you can do in a similar way to eliminate the 1/2 curve?
Well, the 1/2 is yeah, it's coming exactly from what you're saying, from the fact that when you take a square of something, here we have squares of things, right? Square of E, square of A, square of B. These squares over here. Where am I? Okay, these objects. These are expressions which can be written down in terms of the A dagger or BB dagger, whatever it is. When you square them, it's ambiguous. The order in which you take the square is ambiguous. It will be an E dagger E or an E dagger, or a symmetrization of the two. So there are some tricks that you can play to get rid of the 1/2 that way, if you wish. I think it's dirty though. I like it to say that there is this problem. If I write it as E dagger E, eventually I'm going to get a B dagger B or A dagger A plus A dagger. And if I want to express this as A dagger A only, then I can commute one of those products and I get a 1/2. Plus or minus, depending on whether I do A dagger A or A dagger. So but there is that ambiguity floating around. I don't know if I have it here. Anyway, that's what I want to do next. I think it's somewhere over here, but we'll do it next time.
Okay. So for the moment, we accept the 1/2.
Yeah, well, I like it because if you view the field as a collection of harmonic oscillators and you quantize them, then you're bound to have the ground state energy of those harmonic oscillators.
Yeah.
And we know that vacuum is not an inert medium. As I said, somebody said once, vacuum is a very nice material. It's not inert. There's a lot of stuff going on in vacuum. So dragging the 1/2, I think gives a inkling that there will be some action in the vacuum. Okay, so that's why I like it.
Okay.
Okay, if not, no other questions. If not, have a good week. I guess happy Easter for next week, and talk to you in April then.
Okay.
Bye-bye.
Thank you and
Ciao.
bye-bye.
Bye.
Ciao, grazie.
Ciao,
Ciao, ciao.
Ciao, grazie.